All right, so now we're going to look at problem number 19. This is really the last problem, the last slide that we have here in this chapter. And chapter 5, as we know, was dedicated to looking at mechanism design. And it's really up to this point, we've been given all the lengths of the links. We've been given the RPMs. We've been, all that kind of stuff. But in this case, we're going to have a little bit more, if you would, creativity that we can exercise, and we're going to be able to pick some of these values based on the prescribed motion. Okay, that's going to help us. So I want to walk through this problem number 519, because this is going to be similar to the homework problem that you have, the very last homework problem that you have, which is going to be 520 for this module. Okay. So we're going to find problem number 519 on page 120, and we're going to be designing a crank rocker mechanism this time using the information found in that problem statement. So we need to specify the lengths of each one of the links in that 4-bar crank rocker mechanism. So it's an L1, L2, L3, L4, and a crank speed, So let's go take a look underneath our camera what information we are given. Okay, so we're going to be looking at 519 right here. They're giving us a Q. So kind of thinking back, Q is equal to our time ratio. And that's going to be kind of comparing our outward to our inward motion. Now, in this case, since it's a crank rocker mechanism, instead of it being a linear stroke in and out, this is going to be what we call that throw. So it's going to rotate about a fixed center, but it's going to like have an angle to one side and then back, and one side and back. So the furthest part outward is going to be one direction, and the furthest part inward is going to be the other direction. And when we have a Q of 1, that just means that it's symmetrical. So the time to get to that outer throw angle to the inner throw angle on either the out or the in is going to be exactly the same. Okay. And that's going to be just like when we had like what we call an inline crank. Okay. A crank slider mechanism like we had earlier in our lecture. You'll notice T here that's given to us. This is the total time of one revolution of our crank. Okay. So the total motion here back and forth to do 78 degrees of total throw angle is going to be 1.2 seconds. Okay. So these are going to be our givens. These are going to be our givens. So I'm going to start with just identifying this is problem 5-19. And again, this is going to mimic 520, but different numbers. Okay. Different numbers. So, so we know that our Q is equal to 1. We know that our T, which is 4, and I'm going to put cycle down here. So it's one revolution of our crank is 1.2 seconds. Okay. And then we know that our throw angle, they're calling that theta 4, because it's really on it's going to be the angle for which our link number 4 is going to actually go through, and that's going to be 78 degrees. 78 degrees. So but before we really even look at and talk about the numbers here, I do have the AutoCAD sketch that I made for this up. Now, don't worry again. Oh gosh. I'm doing Creo. So don't worry at all about the length of any of these at this time. I'll talk about how some of these were arrived at and how others were calculated. But what we have here is we have a 4-bar mechanism. Link number 2 is going to be our crank and going to be going around in 360 degrees. Then it's connected to link number 3. And then link number 4 is that output that's going to actually be going through that throw angle, the 78 degrees. So you'll notice that I have 78 degrees total. The white is like the extreme position when we're on our outward. And then the center line here is on the extreme position on our inward. Okay. So the difference between those two. So this is link 4 in its outward and link 4 in its inward is 78 degrees. That's the entire throw. Okay. Now, So this is what our 4-bar mechanism looks like. I assumed, and I made the decision that our pivot points for link number 2 and link number 4 were going to be in line with one another. Okay. Very traditional to what we've seen on other mechanisms. And so this is going to be kind of our base, if you would. So let's kind of look back underneath here and see what else we've got. Now, they also want us to calculate what the crank speed is. So we need to find W of our crank. Okay, that's going to be a question mark. We're going to need to determine now L1 is always going to be an offset. All right, since this is going to be in line, meaning that our position for the crank center of rotation and the position for the output or link number 4 center of rotation, they're in line with one another. L1 is actually going to be 0. So we don't have to worry about that. That's always an offset. Okay, so I'll put here offset. All right, so there is no offset. We have those in line with one another. And we're going to have to find what L2 is, L3 is, and L4. Okay. L2, 3, and 4. And I'm gonna make a sketch of, rather than going back to AutoCAD each time, I'll kind of make a sketch of our mechanism. Okay. And this is going to be link number 1, 2, 3, and 4. Okay, so just kind of giving us that pictorial of the type. So link number 2 is going to go all the way around, considered a crank. And then link number 4 is going to rock back and forth. And the angle for which it is going to rock back and forth is that theta 4, which is equal to 78 degrees. Put this up here a little bit. Let's get out of the way. .78 degrees, which is what the problem gave us. Okay. Now the entire time for this to go around 1 revolution and this to go back and forth, that's our cycle time. That's going to be T is equal to 1.2 seconds. Okay. And then Q equals 1, as again, as we had stated earlier, this is symmetrical motion. So it's the same amount of time to go out as it is to go in, out and in. And that's because these are in line with one another. Okay. Now, let's calculate our crank speed right away, because that we have everything that we need to do that. So to calculate the crank speed, just like we had for our other problems, so this will be step number 1. W of our crank is going to be equal to 1 revolution divided by the total time to complete a cycle. Okay. And I think we always had a delta in front of there, the change in time or the total amount of time to go 1 revolution. So to do that, we're going to say 1 revolution divided by 1.2 seconds. Okay. So if we get our calculator out here, we're going to take 1.2 divide, and we're going to get 0.8333 revolutions per second. Okay. And that's going to be our W. Now, as we know, that's not like the units that we normally express angular speed in. So we want to change that to RPMs. So our W of our crank is going to be equal to 0.8333 revolutions per second. And we just want to convert that to revolutions per minute. So all we need to do is we're going to take 60 seconds, put that on top, 1 minute on the bottom, cancel each of those out. And RPM wise, this is going to be 50 RPMs. Okay. And that's going to be our W of our crank. So that's one of the answers that we need. Okay, one of the answers that we need. It's not 8, it's 0.88, 8.8. And then, oh, it's an S and then crossed out. That's what that is. Yeah. I'll put the seconds underneath there. Okay. So that's one of the things that we needed to find. So we're done with that one. Okay. We already determined what our L1 is because there is not an offset from, between the center of this and the center of that. They're not offset. They're in line with one another. So L1 is going to be equal to 0. Now what we need to do is we need to determine the lengths of our links. Okay. Now, as we look at the equations in the book that are available to us for this section, and those are going to be found, this discussion of design of the crank rocker mechanism starts on the bottom of page 115, okay, very shortly, and then it continues and gives us the process on page 116, okay? So this kind of walks you through. I'm not going to read each one of these steps, but we're going to informally go through this entire process. Now, equation-wise to find different lengths, okay? So, for instance, down here, equation 515, it says L2 is going to be equal to 1/2 AC2 minus AC1, okay? Now, let's find where A and C1 and C2 are. So as we look here, A is the center of rotation of our crank, okay? Try to scooch in here. And C2 and C1 are at the extreme positions of that throw angle on the end of our link number 4, okay? So here's where link number 4 is, and here's C2, and here's C1. So A to C2 is right there. A to C1 is right there. And those are the lengths of the lines that they're referring to. So it would be measuring that out, okay? Now, in order to really do this calculation, we've got to like start where, where we know something or we can identify something. So what I did and what it kind of goes through this process and tells you to do, you're going to need to assume a length of link number 4. So that we can figure out like exactly where that is. You're also going to need to determine what is the distance between our two values here, or our two centers of rotation, if you would. So what I did for our problem, and we'll go back to AutoCAD in just a little bit, I assumed this distance right here was 6 inches, all right? And my length is 4 inches. All right, so that's going to be my L4. It's going to be my L4. You as the designer, when you have a practical application out in the field, you'll have these like, what is the space that I have? Okay. But for right now, for these problems, you'll notice that there aren't answers in the back of the book, except for like for the W, we can figure that out, right? But by the information. But after that, these numbers get to be things that you get to decide, okay? As long as you're meeting the requirements of one cycle, the throw angle, and your Q, okay? After that, you get to figure the rest of this out, all right? But once you decide on something, for instance, like now deciding on L4, now I'm sticking with that. Now L4 is going to dictate where that C2 and that C1 are going to be, right? Okay. So what I did was in AutoCAD, just so that you can kind of see the construction here, on my link number 4, or where my my center of rotation is for that link, I went straight up vertically and then half the distance of 78 in one direction and half the distance in the other direction, so that I would have my full throw, so it would be even on both sides. Okay, that set up then, if that was 4 inches in length for link number 2, that set up my C2 value there. Do you see that? Okay, and then going back to the 78 degrees, here's my C1 value, okay, or my position. Right? Point A is here. So now what I need to do is I need to measure all the way along A to C2. All right. And I believe I have that number right here. It's 9.067. 9.067. So I'm going to use that equation to find the length of L2. So my number 2 here is, you're going to assign L4. Okay, and the distance between centers, which we just did. Then our step number 3 here is we're going to calculate L2, and we're going to use that equation that we just saw. Okay, so L2 is going to be equal to 1/2 times A times C2. That's the length from the center of rotation of link number 2 all the way to the endpoint of link number 4 in its furthest out position along that throw, minus A C1. Okay. And that's where you're going to have to do some of this construction in AutoCAD. So going back to, well, I'll write the equation first. 1/2 times A times C2 minus A times C1. So going back to AutoCAD here, my A all the way to C2 is the 9.067. Okay. So it's going to be 1/2 times 9.067 inches minus the length of A from A to C1, which is 4.668. I'll zoom in here a little bit so you can see those numbers a little bit better. Okay. So then now going underneath here and working those numbers, 9.067, 4.668, subtract, and then take half of that. So my L2 is going to be equal to 2.1995 inches. Okay, 2.1995 inches. So if we go back here to AutoCAD, let's see. I it rounded because I put it in there as 2.1995 as a 5th decimal place. So because it's a 3-place decimal, it rounded it to 2.200. Okay. So that is in there at that length. So now you're going to notice that I know what my link number 2 is. I know where that position is. So link number 3 now, how long is it? It's going to be the difference between those two, right? Link number 3. So I can, up on the top here, I can put my link number 2 is equal to 2.1995 inches. Got that one done. And then link number 3, I am simply going to measure it. So if I do an aligned dimension from this center, oh, grab the wrong one. It's on my dimension layer to the official. I'm going to go from that center to this center. And it looks like my length is 6.867. 6.867. So I'm going to put that up here. And then my link number 4 is 4 inches. There we go. I go back underneath here. And so this problem, although it's not as, I don't think it's, I'm not going to say it's hard. I don't think the other ones are hard. It's just that there's more steps to the other ones because especially when you have a Q equal to something other than 1, now you've got to figure out what those times are, the T1s and the T2s. So there's a little bit of math there. But the thing to know here is, because usually you can look at a problem like, okay, now where do I start? We had to assign an L4 and a distance between the centers before we could really go any further. We had to know that information. And then using your link number 4, we could then use that throw angle, that maximum throw angle, and then distribute it on either side of the center line, if you would, from link number 4, as if it would be like straight up and down. And then we just use AutoCAD to determine the rest of the values. And then in this one equation for L2. Okay. So any questions about that? So that's an example of this type of a problem. So the one that you have assigned for your homework is very much the same. Okay. Except, so you've got a Q1, you've got a theta 4 max. This one's going to be 100 degrees. And then your total time to go around in the crank to go around for one cycle, you get 3.5 seconds. Okay, 3.5 seconds. And then you need to specify your crank speed. That's going to be your W. And then these values here as well, the same process that we just went through. Okay, so again, you get to assume, you know, what your values are. If you want to do a metric problem, you could do it in millimeters. If you want to do it in inches, you can do it in inches. And that's where, like I said earlier, your W, you can check the back of the book, but it won't have any other parameters because it all varies depending on what you choose for your design. All right. And I know it feels probably a little weird to be able to be like, okay, I don't know what I want to do. Just pick some values. All right. For a type of a mechanism, you know, just some numbers in there. Okay. All right. So that's our last problem. So let's briefly go over, our homework. So you'll now be ready to take a look at the homework that's assigned. So let's look at assignment number 7. And as we said, 520 is going to be that last problem that's going to mimic the problem that we just finished up with here. 12 and 16, those are going to be those crank sliders. 12 is going to be an inline crank slider. And then 16 is going to be an offset. So again, the last time we were together in part 1 lecture, if you need to look back, we did examples of each of those. And then numbers 4 and number 2, those are calculating betas and Qs and Ts. And those are going to be similar to the example problems that were in the actual chapter as well. So we took a peek at those too. So at this time, you are ready to do all of these problems. And I think you have some good resources and examples to draw from. And you have me available to answer questions as they come up. So before I stop recording, are there any questions as we're kind of looking at things? All right. So then what I'm going to do is I will stop recording, but I'll be available for you to ask any questions that you might have.